Good morning. Okay, so I'm here to talk about KNFT conformance testing as minimum requirement to safeguard interoperability. So it is already well known that Bosch has launched KNFT update from protocol CAN, and for sure this protocol brings a lot of new functionalities, all good things, and due to this reason, the OEMs are, I guess, highly interested in this new technology. And on the other side, of course, there are different vendors, providers, that are willing to provide the OEMs with different solutions. Then, the question here, always having in focus that we are talking about interoperability. How are those applications from different vendors, from different providers, how those applications are going to work when interacting together in the same net? We could look back into previous experience, and we could think about, just to mention a few examples, CAN, Link, or FlexRay, and we find actually that interoperability is actually not guaranteed, just from previous experience. Now the question is how to prevent non-standardized behaviors, how to prevent non-interoperable behaviors. This presentation hopefully will bring some answers about, about those points. And here is a little agenda, so we have an overview. First, I would like to talk about interoperability problematic. Then I would like to explain what actually brings conformance testing into interoperability. Then I think it would be useful to see a little bit about the procedure, how to draft a conformance test specification from scratch. And having that knowledge will be easier to get to the main focus of this presentation, which will be how the new technology of KNFT, how the new functionalities were implemented or added into the updated conformance test standard. And yes, at the end, I would like to briefly explain also about the structure of this conformance test standard. So let's start talking about interoperability problem description. And in order to do so, it is important to start talking about standards. I guess it is already pretty clear why standards are created. The most important point, I would say, to share development cost, as we see here in the list, also to improve quality, to facilitate innovation, to increase speed to the market, all good things. But I would like to focus on what are actually the main problems that often arise from standard. As we see here, specification can be ambiguous or not clear enough. And just when thinking about it, human language is actually already ambiguous, so why not a standard is going to be ambiguous? Then the main problem is that this could lead actually to different interpretations. Let's take a look deeper. Here we see an example. 3 different suppliers have taken as reference the same standard. Supplier A, B, and Z. Supplier A has a missing part, supplier B, additional part, new features, and supplier C, adapted solution. So there is a high chance that the same products from the same vendor will interact with each other with, we could say with no problem. That is not our focus. Our question is actually how are those 3 different solutions going to work together? Second question, as we noticed there, those different 3 solutions are not fully aligned with the standard. Then what to expect when all those devices are actually working together? I guess the first answer could be non-standardized behavior could be observed. That is actually not what we want. Now let's take a look to interoperability. What is it actually? and what brings conformance testing into interoperability. Now, interoperability is a property referring to the ability of a system or a device to interact with another system and other devices all together in the same net. Then, when we look at it from the perspective of standard, we could say that interoperability is a result of adherence of implementation to their specific standard. Now, what brings conformance testing into interoperability? Conformance testing for sure will not change anything into the device we are testing, into the system under test. For sure will not do anything of those things. But after applying conformance testing to a certain device, if that device is approved by the conformance test, then there is a higher chance that this device will interact with another device which have also been approved by this conformance test. Then we could summarize that conformance testing is the minimum requirement to guarantee interoperability. Why to risk then? Okay, having said that, let us suppose that we want to draft a conformance test right from the scratch. What is the first challenge that we are going to be facing here? This is going to be the testing dilemma. Testing dilemma states that it's actually not possible, it's not going to be possible to test each theoretical test case, each theoretical parameters or scenarios. If you imagine all the things that could be tested, at the end we could get to the conclusion that there is a huge amount of test cases. And one of the most important points that I would like to explain now, it will be useful for the next slides also. Conformance testing needs always, as reference, a standard. Without standard, we cannot have a conformance testing standard. Yes? So the key question here is, how could we, when starting to with the planification of the drafting of a new conformance test, how could we guarantee that we are going to have the maximal coverage of the standard with the minimal effort? How to guarantee that not significant test scenario is going to be left aside? Okay, there are some methods that could help us in order to guarantee all those points. Let's take a look on these methods. So the first one is pretty basic, tagging. As the name says, it's no more than tagging all the testable items that we find in a standard. As we see here, here is an example from FlexRay protocol conformance test development. Down there, there is a little piece of standard, and as we see there, there are some tags with name, really important, then we know where this tag come from. And those tags, those testable items, were integrated into the test, into a test case, just an example, that is the a flow chart, and it shows how different tags were integrated. If we have done everything all right, after running the conformance test, we can make sure, we can be sure that at least we have visited at least once each testable item. But after applying this method, always what we get is just a huge list of requirements. Then we need maybe a second method in order to organize them systematically, to give a little bit more of structure. And here, this second method could be used system operational vector space. This is about taking into account all the different variables that we could find in the testable items from the system that we are going to test from the product, and putting all those variables within different vectors. Each element of the vectors, as we see there in the example, are different variables. And within each element of those vectors, we could define sub-vector spaces. For example, if we take system configuration, then a sub-vector space will be composed by different elements like baud rate, termination topology, environmental conditions, and sub-vector again, temperature, moisture, and so on. So what we get here, again, if it's really good implemented, we could play with all the different configurations that we could imagine, and as a result, we will obtain all the theoretical cases, all the theoretical values, scenarios, parameters that we want. But as we said first in the testing dilemma, this could be neither technical nor commercially feasible to try to cover. This is an enormous amount of effort. Then, okay, we have here a method that will allow us to know about all the theoretical combinations, and there are two possible solutions to reduce this huge amount of possible test cases. That means some parameters could be left as constant. Just an example, temperature and moisture. They could be left as constant values. Doing that way, we reduce the amount of possible test cases. And a second possibility could be to take actually a certain range of parameters. Again, only an example. We could take, for example, maximal values, minimal values, that means corner conditions, and average values. Then we are taking the most representative cases. Doing that way, we get already a little bit more organized. We have given a structure to the conformance test standard, and I guess we are ready to see how to go from the standard to conformance test specification. Just an example. Then, as said before, it is always necessary to have a standard as reference. Without standard, we don't have conformance test specification. Then, from the standard, we are going to obtain the requirements, which is no more than a huge list of testable items. In order to obtain that, we are going to apply tagging method. This is actually a real example. This is the standard, the ISO 11898, part 1, which has been tagged. I wanted to show it. And then, of course, after having those requirements, those testable items detected, we can organize them by applying the system operational vector system space. Then after that, hopefully, we get our test cases, and the group of test cases will make the conformance test. Now, one of the most interesting points, I guess, how could we do to update the previous conformance test with the new features with the updated ISO 11898? And okay, first step, logical step, was to detect what is new actually. What are those new testable items? Then we apply the same methods. New requirements are detected with tagging, then system operational vector space, and then we get the new CANFT test cases. Now, how to implement those new CANFT test cases into the previous conformance testing standard? Such a big question. I think there was a working structure, and why to change it, actually? If it was working, doesn't make sense to change the structure. Then the answer was actually really simple. We integrated the candidate test cases into the previous conformance test specification, and respecting always the structure. The previous classic CAN test cases remained as they were, and the new candidate test cases, when possible, were integrated into the classic CAN test cases. When a new functionality is there, then a new test case was created, as we see here. And there are also some old or previous classic CAN test cases that were actually left as they were, no modifications. Then, after this, the new conformance test with CAN-FT coverage is there. Now, I wish it was so simple. Actually, there is a lot of more work to do. Why? Because till now we have obtained a list of requirements, then we have organized them systematically. But I guess this is still not enough to talk about a full conformance test specification. We need to provide more useful content. So then test engineers are able to take those test cases and go ahead through the different test cases. Then I would like really briefly to explain about some fundamentals that must be kept into account when drafting a conformance test. So, as we see here, the test cases, environmental conditions, test system, and also the methods that are going to be applied shall be specified abstractly. We don't want to specify there that we are going to be using a certain oscilloscope or a certain instrument, but we could talk about bandwidth or some other more subjective requirements. Then, of course, comparability, clear and repeatable test sequences leading to comparable test results. And, of course, the test cases should be also specified in a way that the same test environment will run for all the different implementations. And in order to accomplish with that point, then we have also to consider that there could be different possible configurations in order to be adapted for different possible IoTs or system under test. I think a must here is that after repeating over and over and over again the same test case, it is highly desirable that we are going to get the same result. No question, I guess. Then there is a second point that is really connected to repeatability, which is the following. It is, of course, important to know about how the test goes. If it was a pass, fail, no question about that. But in order to make this test case repeatable over and over and over again, it is really necessary to clarify the starting point. That is really important. And for sure, in order to know how the test was, if it was a pass or a fail, we need to be really clear about which signals are going to be recorded during the test case, how the system should be actually observed. This is not only about running the test at a certain point of time, but then maybe we want to come back to the test results, and hopefully all the observed signals information are still there, so we can go ahead and without maybe having to run the test case again. Just an example. And of course, unambiguous results. I think the most important point here is how to classify the outcome of a test case. Just imagine that you have, okay, this test case is going to be qualified as pass just because the IoT behaved as expected. That says actually not so much. Then one of the goals here is to be very detailed in the information that we provide, how actually to get to qualify that the result of a test case can be qualified as pass. Fail, I guess it's really clear when we observe a deviation from the standardized behavior. And 2 more points. It could happen that a test result is inconclusive or we find an error. That means inconclusive, for example, the starting point could not be set. Or an error could be that there was a failure in the test system. Then the procedure here should be suggested to be correct the problem and run the test case again. So now, very briefly, I would like to show how the new KNFD test cases impact into the structure of the new conformance test specification, ISO 16845. Now, as we see here, it's all about grouping. This is the same structure that was used previously with, I guess you already can notice some new things there, test cases. And of course, those test cases are always grouped. And in order to add planning, development, understanding, test execution. Now, the first layer that we are going to find here is test types. We have 3 kinds of test types: received frames, transmitted frame, bidirectional frames. Those types are just to test the behavior of the IoT when receiving frame, transmitting frame, or when the communication happens in both directions. Within each of those test types, there were previously 7 different test classes, and now, as we see here, we have a new one, the class number 8, KNFD bit timing class. So what brings actually this new class? This new class is to test, to cover all the specific new functionalities that come with KNFD at the level of time quanta. Of course, there are different test cases from KNFD within the other test classes, but class 8 is exclusively to test the new functionalities of KNFD at the level of time quanta. Now, last but not least, the test cases. As explained before, class 1 to 7, we find the different test cases when possible. Again, KNFD test cases were integrated into the classic CAN test cases. And when that was not possible, new test cases were made, and the other ones, like we see at the beginning, were left just as they were. Class 8 is only about KNFD test cases. We could even go deeper and talk about elementary test cases, which are only a repetition of the same test case, but within a different parameters ranges. Now, as a conclusion, then it is a fact that standardized specifications can be interpreted in different ways. That is a fact. That will lead to have applications with similar but not equal behavior. Then how to prevent this situation? They must be actually interoperable. That is, I think, one of the main goals here. And I guess at this point you may be already the answer. Of course, conformance testing is the answer. Now, as closing point, I would like to share with you SOVS group, after applying this explain method, has drafted and elaborated a new conformance test specification for data link layer, which is intended to become an ISO standard. And the current point now is that this document is being revised by, the technical points are being revised by the CANFD task forces. And yes, I'm happy to say also that the test system from SOVS has been already updated so it can test CANFD protocol, and it is now in a phase of validation, but hopefully we are starting to offering also CANFD coverage for testing at the beginning of the next year. So thank you very much for your attention, and I don't know if you have questions.